So what I'm going to talk about is what we're most recently doing in the laboratory. We are exploring how the ERG channel increases intracellular calcium concentration in myotubes. And what we have found so far is that it does appear to modulate IP3 signaling. So let me give you some background. The ERG1 voltage-gated potassium channel is a tetramer of 4 alpha subunits, just like the typical voltage-gated potassium channel. Each unit has 6 domains, membrane domains that go across the membrane with a voltage center. The ERG has 2, but there's actually more, but there are 2 main alternative splice variants, ERG1A, ERG1B. They differ in their N-terminus amino acid makeup and structure. The ERG1A and the ERG1B are together make up a heteromultimer in the heart that is responsible for a repolarization of the action potential. However, what we have found, and just by accident, was that ERG1A, that's the only alternative splice variant that we find in muscle. And we only find it prominently expressed in muscle that is atrophying. In fact, it was originally reported that it wasn't found in muscle and we were using it as a negative control. But we find it in muscle that is atrophying in response to hind limb suspension and denervation and calcium cachexia, cancer cachexia. We find it not only with immunohistochemistry, but also with Western blotting. You'll see here we've got the suspended muscle. We've got the 2 glycosylated variants that is absent basically from the control muscle. We can find it in control muscle, but we have to go to heroic efforts and really concentrate our cell lysates. So we wondered, obviously, what is it doing? And just briefly, what we have published a couple of papers on is the fact that it appears to be participating by upregulating protein degradation. We did some electroporation of MERG into mice that were weight bearing. And what we find is that ERG overexpression actually increased UPP pathway activity. When we put a defective ERG1A variant into animals that were suspended and would, in control situation, undergo atrophy, we found that the ERG would interfere with the UPP activity and decrease it by 15%. The obvious question is how? How is it affecting UPP? And we thought the simplest place to start would be looking at skeletal muscle specific E3 ligases. And indeed, what we have found is that in both C2, C12 cells and mouse skeletal muscle that are overexpressing ERG, there is an increase in not only the mRNA levels, but also the actual protein abundance of the E3 ligase MERF, but not atrogen. Now, the mechanism by which ERG causes an upregulation of MERF is something we're investigating, but I'm not going to talk about that here. And quite frankly, the funding agencies have not been as interested in that as they are in what we have found and published recently also, is that ERG expression increases basal calcium concentration and calpain activity. It does this in both the calpain activity is affected not only in the myotubes, but also in mouse skeletal muscle. Here by this slide, there are a number of possibilities. However, because the ERG channel is found in the sarcolemmal membrane in heart, and we've also shown that it is in Sandra Zampieri and I have shown that it's also in the sarcolemmal membrane of the skeletal muscle. It's also found in the T-tubules of heart, and we have some data suggesting that's also the same with skeletal muscle. We just got to follow up with some EM work and confirm that. But because of its proximity to the CAV 1.1 L-type channels, we thought it may be affecting L-type channels. So that was the first thing we did. So we're working with myotubes. We're using a virus to transduce them and cause them to overexpress ERG. We're also using a control virus and transducing control cells. And what we find is that overexpression of MERG does indeed induce greater calcium transients in response to depolarization. So we decided, rather than just looking at basal levels, we look at depolarization, looking at effects on the membrane because of the fact that the CAV 1.1 channel is in the membrane. So we find that there is a significant increase, and that when we treat these cells with a specific ERG blocker, astemizole, and subtract out the astemizole sensitive current, we find indeed that this astemizole sensitive current, this calcium transient, is greater in the ERG than in the control cell. So we have confirmed that it is indeed, ERG is indeed causing there to be an increase in intracellular calcium in response to depolarization. So what we wanted to do next was look at the specific current, L-type current density. Ranging from -70 to +50, and this was done in Dr. Greg Hockerman's lab. What they find is that there's no difference in the actual current density. So we also did some Fura dye studies where we had cells that were transduced with ERG and the controlled, and we depolarized them in the presence of and not in the presence of both nifedipine and nicardipine. These are specific blockers of the L-type calcium channels. And what we find is that when we subtract out the nifedipine and the nicardipine sensitive current, there's no difference. So it appears that ERG is not affecting L-type channel currents. Also did some work with Western blotting and cells that were expressing hours over time after transducing with the virus. There's no change in either the protein abundance, which would be the most telling piece of data, nor is there an increase or a change of any type that's significant in levels of mRNA after 48 or even 60 hours of treatment with the HERG. So it appears that the ERG is not affecting L-type calcium channels. So the next question was does ERG modulate release of calcium from intracellular stores? And we used the, again, the same model, the ERG treated cells versus the control. We depolarized them in the presence of and not in the presence of a circa blocking reagent called thapsogardin. So this would cause the intracellular stores
Amber, your connection is very
would be blocked. And what we find is that when we look at the thapsogardin sensitive current, when we subtract it out, what we find is that indeed there is an increase in intracellular calcium in ERG expressing myotubes. It is sensitive to the circa blocker thapsogardin. You can see here we've got the ERG intracellular levels versus the control response to the depolarization. So we are concluding that it's affecting intracellular stores. So from what intracellular store does the ERG-induced increased intracellular calcium concentration derive? And we've got a variety of possibilities that we're looking into. Could be the ryanodine receptor, could be IP. First, we're also working on the other two, but it was simpler to go with the IP3 first. IP3 signaling, as you know, is when there is a phospholipase C that takes IP2, converts it to IP3, which then goes to the receptors that are on the sarcoplasmic reticulum, and that then causes release of calcium from the SER. What we were thinking is that ERG would have some effect on this signaling system. So the first thing we started with was looking at, does it affect phospholipase C activity? So we used a blocker of phospholipase C, a U7 reagent, and using again our ERG treated cells against our control treated cells. And in this time, what we decided to do was to elicit a calcium response using bethanechol rather than the depolarization. The thought being is that bethanechol affects muscarinic receptors and thereby turns on IP3 signaling. So we know that we are inducing calcium, and we see in both the control and in the ERG treated cells we get a response to bethanechol. There is an increase in intracellular calcium, and it is greater in ERG. And what we find is that in both, the U7 causes there to be a decrease. It blocks. So what we know is that this U7 will block PLC. So some of the intracellular calcium increase is due to the phospholipase activity. However, when we subtract out the U7 sensitive calcium response, what we find is that there is no difference in the ERG treated cells versus the control, at least nothing that is significant statistically. So the increase in intracellular calcium in ERG expressing myotubes is not sensitive to the PLC inhibitor, suggesting that regular modulation of phospholipase C does not contribute to the ERG mediated increase in intracellular calcium. So what we thought, well, could it be modulating the receptor itself, the IP3R1 receptor found in skeletal muscle cells? So we went to single cell calcium imaging here. And we could have done this with the U7 also. We tried. However, what we find is that at the single cell level, the U7 causes some fluorescent background with the fluorides, and we're going to have to work around that. But while we were set up to do the single cell calcium, we thought, well, let's go ahead and try our zestospongin C. This is a compound that is an antagonist of IP receptor 1. So what we find is that with single cell imaging with the FURA2, we find that this increase in calcium that responds to bethanechol is blocked by zestospongin, suggesting that the ERG-induced increase in calcium resulting from bethanechol is inhibited by treatment with this receptor, so that it suggests that ERG modulates IP3-1 receptor activity. This is quite exciting, and we've actually started looking into some known modulators of receptors. ERBIT, for example, is a known modulator of IP3 receptors. We don't find any change in ERBIT, so that's one way that we know it's not working, and we got to find out how it's working. So our conclusions are that the ERG channel does not increase intracellular calcium by modulation of L-type calcium channels. The ERG channel increases intracellular calcium by modulation of intracellular stores. The ERG channel may increase intracellular calcium by modulation of IP3 signaling, specifically by modulation of the IP3 receptor 1. Now, interestingly enough, work I've done in the last 2 weeks, I've had a student lose a parent and they've taken a leave of absence. And so I've taken over doing the studies myself. And what we have found is that there's no effect apparently on store operated channels, but there does appear to be an effect through the ryanodine receptors. So what it is when we set up our same study, we got the different myotubes, some are expressing ERG and some are controlled. And we do our FURA2 assays, and we use caffeine to increase intracellular calcium by activation ryanodine. What we find is that it looks to appear so far, I've got to do more replicates and do better statistics, but it appears indeed that ERG is modulating ryanodine receptor activity. And in fact, I've just got a blot that shows that it will interfere, ERG does interfere with the abundance of calsequestrin. So I actually think the ryanodine work is going to be, especially for skeletal muscle, is going to be a really exciting area that we're about to open up. So acknowledgements. Of course, now this work is done in conjunction with Dr. Greg Harkerman, a brilliant scientist at Purdue, without whom I would probably, in fact, I know I would be lost in the calcium realm. Lab members include Dr. Winhorn Wong, Dr. Evan Pratt, Kyle Harvey, Clayton Whitmore, Luke Anderson, and Britton Cobb. Most of this work was funded by the United States Department of Defense, to whom I owe a great big thank you, and Southern Illinois University School of Medicine. And I want to thank you all. Are there any questions?
Thanks, Amber. Thank you so much, Amber, for your patience. We'll take some questions. Anybody have a question out here? No?
Everybody's tired, I'm sure.
Yeah, end of the day, you go
Right,
drives
right.
us very hard out here.
And
Thank you so much,
yeah, and I
Amber.
want to thank the people doing the video stuff. I know we couldn't hear Simona, but her slides were so well put together that I could follow her talk without her. Her slides were amazing.
Ciao Amber.
Thank you
From
all.
Ugo. I am Ugo. No.
Hi, Ugo.
Hello.
I'll see you next year.
Yeah, we all,
Wait for you. We wait for you next year. Thank you.
We'll be there.